Dear students, I am Rajiv Kumar, Assistant Professor in the Department of Electrical Engineering in Asansol Engineering College. Hope you all are doing well with your health and studies during this pandemic and lockdown period. Till now, whatever I have discussed with you all through Google Classroom, I will start explaining all those topics serially through this YouTube platform. So I request all of you to follow my video lectures sincerely. I request you to go through my PDF notes which is already provided to you after listening to each session. We will be also having interaction session for doubt clearing on Zoom platform. You can place your doubts in comment box or in Google Classroom. I will start the session with unit 5, that is transformer. Hope you will enjoy the video and learn the topic sincerely. Dear students, we will start the topic transformer. Okay, so in transformer, in our syllabus, both single phase and three phase transformers are included. So we will first conclude this single phase transformer. We'll first learn this, then we will start three phase transformer. Okay, so in today's lecture we will cover these points mainly. Okay, the definition of transformer, what is the principle of operation of transformer, basic theory of transformer, EMF equation of transformer. We will derive this actually. Okay, and the next is voltage transformer ratio, which is denoted by K, and we will see a few related numericals. Okay. Now see, what is transformer? Okay, so the definition of transformer is electrical power transformer is a static device which transfers electrical energy from one circuit to another without any direct electrical connection and with the help of mutual induction between two windings. It transfers power from one circuit to another without changing its frequency, but maybe in different voltage level. Okay, so see here, we can see that we have two different coils or windings, you can say, right? This is, what is this? This one is, this is core. This is called core, which is made of silicon steel, which is made of silicon steel. Okay, silicon steel. Okay, we will later on see that this core is not a simple core, right? It is actually laminated. Okay, it is laminated, and I will explain it why it is called laminated and what is the necessity of this lamination. Okay, so this thing I will explain later, right? For the time being, just note down that this laminated core is used to reduce eddy current loss. Okay, so that you keep in this mind, I will explain. Fine. Now see, this is the core. What is the purpose of this core? This core is used for the conduction of magnetic flux. Okay, magnetic flux. Right, so this is the purpose of this core. Okay, now see, we have two windings, two different windings. This winding and this core is actually common to both the windings. Okay, now regarding basic theory of transformer. Okay, so for basic theory, the working principle of transformer is very simple. It depends upon Faraday's law of electromagnetic induction. Mutual induction between two or more winding is responsible for transformation action in an electrical transformer. Okay, and you know the Faraday's law of electromagnetic induction very well. Okay, so see here, this is primary, this is called primary winding, this is secondary winding. Okay, so let us suppose that the number of turns in this primary winding is n1. Okay, and the number of turns in the secondary winding is, let's suppose it is n2. Clear? Okay, now see, in this primary side, as we call it as primary because we will give input to this side and we will get output from this side, so this is called secondary side. Okay, so now see, in primary, when we connect AC supply, okay, when we connect a AC supply, what will happen? Okay, so let us see. Since we have applied a AC supply which has some frequency, right? It has some frequency having some voltage, certain voltage. Okay, generally it is 50 hertz in our case, right? So see what will happen if we give AC supply. Since it is a closed circuit, so a current will start flowing. Okay, current will be set up in this coil. Okay, fine. So let us say this current is I naught. Okay, I naught. It is actually no load current. Why? Because we have not connected any load to the secondary side. So that is why the current which is drawn in the primary winding or from the source in the primary winding, when there is no load connected to the secondary side, so this current is named as no load current. This current is very low actually, right? This is very low current now comparative to the full load current of transformer. Okay, now see, when it is, so due to this current what will happen? Okay, try to understand this step by step. Now if this, when the I naught current is flowing in this coil, so what will happen? Okay, so we know that whenever a current is flowing in a conductor, due to this current magnetic flux is being set up always, right? We know this concept that if you give DC supply, for DC supply in the coil, okay, say this is a coil and we are giving DC supply. Okay, so in this, what kind of magnetic field will be generated? It will be a constant magnetic field, right? Constant magnetic field. And if instead of DC, if we are giving AC supply, so what will happen? It will develop a alternating magnetic field. Alternating magnetic field. Okay, so in our case, since we are giving AC supply to this coil, so obviously it will develop a alternating magnetic field or flux. Okay, so that flux is, this core is the will act as the path for this flux. Okay, so that flux will set up in this core itself. Okay, let us say we are denoting by phi. Okay, so this flux is being set up in this core. Okay, and we know that this flux is due to this I naught. Okay, now let us try to understand the nature of this flux. Okay, so as we explain that this will be, the nature of this flux will be alternating one. That means it will be alternating in nature like this. Okay, it will gradually change its magnitude with respect to time. Okay, so now see, now just imagine that this flux has been set up in this core. Okay, now on the same core there are two windings. One is this one, primary winding, another is secondary winding on the same common core. Okay, so what will happen? Fine. So according to Faraday's law of electromagnetic induction, okay, it says that whenever a changing flux is linked to a conductor or coil, an induced EMF will be produced, right? So since this alternating flux, so actually these windings are uh, they are facing some change in flux, okay, linked flux, of course, okay. So this, since this flux is linking to both these windings, okay, the same flux is linking to both primary as well as secondary winding, okay. So what will happen is that in per turn the EMF will be induced, right? In each turn EMF will be induced according to Faraday's law of electromagnetic induction, okay. Hope you are getting my point, okay. So since the induced EMF in per turn is due to this flux only, so what will happen, in each turn the induced EMF will be same, whether it is primary or secondary, whatever, okay. So that means my statement is that EMF per turn, EMF per turn in primary will be equal to EMF per turn in secondary coil, okay, in secondary, you can say secondary coil, okay. So in both these coils the EMF induced per turn will be equal, okay. Try to understand this, right? In per turn I am telling, I am, okay. Now see, so based on the number of turns that there will be a total voltage induced, right? So let us say the total voltage induced is E2 in secondary, okay. This is the induced voltage, right? Okay. And similarly the voltage, entire total voltage induced in the primary is, let us say it is E1, okay. So E1 and E2 are, what is E1 and E2? E1 is, therefore E1 is primary induced EMF, okay. And E2 is secondary induced EMF, okay. Fine. Now see, as we are telling that EMF induced in primary as well as EMF induced per turn in primary is equal to EMF induced per turn in secondary. So what will be the EMF induced per turn in primary? Since this E1 is the total EMF induced across all these turns, okay, fine, and number of turn is given N1. So the total EMF induced across N1 number of turns is E1. So what will be the EMF induced per turn? Obviously E1 by N1. E1 by N1. Okay. Now what will be the EMF induced per turn in secondary? So similarly, okay, we can find that the total EMF induced across N2 number of turn is E2. So induced EMF per turn will be E2 by N2. And as I explained that EMF per turn in primary will be equal to EMF per turn in secondary, so these two will be equal, okay. And the reason is that you should remember that the reason is, since E1 and E2 are induced, or you can say that induced EMFs are due to common flux, due to common flux phi in the core, okay, phi in the core. Due to this reason we are able to write this, okay. Hope it is clear, okay. Now see, this is this is a very important relation, right? We can write this relation like E2 by E1 is equal to N2 by N1. This is an important relation, right? It's very important. Okay, so now we can conclude that once again I am telling you that the basic theory of transformer, whenever we apply alternating current to an electric coil, there will be an alternating flux surrounding the coil, right? Surrounding this coil there will be alternating flux. Now if we bring another coil near to the first one, there will be an alternating flux linkage with that second coil. Okay, as the flux is alternating, there will be obviously a rate of change in flux linkage with respect to the time in the second coil. Okay, naturally EMF will be induced in it as per Faraday's law of electromagnetic induction. So in both these windings, as per the law, induced EMF will be produced, and these are E1 and E2 respectively. Okay. Now let us see what will happen if we load this transformer. If we load it, what will happen, right? So for this I will move to my next slide for better understanding. Okay, so see now, so let me first draw the diagram quickly, okay, for our understanding. Okay, so this is the core I'm drawing, these are the windings. Okay, this is primary winding, now this is secondary winding. Okay, now see, here in this primary winding we have a alternating source AC voltage, right? AC, and this one. So in this condition actually, if we give a supply voltage V, suppose this is supply is V1, okay, so I naught, that is no load current, starts flowing as we discussed earlier. Now due to this flux setup, okay, what happens that an induced EMF in both the coils is being developed, right? Here this is E1, here this is E2, as we discussed, right? The number of turn is of course N1, this is N2. Okay, fine. Up to this we know. Now what will happen? What will happen if I load it? Okay, so see, here in the secondary, you can see that the voltage has been developed across this, right? This E2, but since it is open circuited, okay, that is at no load, so there is no current flowing in this secondary coil. Fine. Now if I load it, suppose I am loading it with the help of resistance. Okay, you can say there is a resistance, suppose. Okay, so what will happen, since this is now a closed circuit, so current will start flowing, right? This is, say, this is I2 current starts flowing. Now see here in this coil, earlier no current was flowing, but now I2 current is flowing, and this I2, the nature of this I2 is also alternating current. Why? Because this E2 is alternating one. Okay, so due to this I2, again a flux will start developing. Okay, a alternating field will develop due to the current flowing through this secondary coil, right? Just like in primary coil, a current was set up by this source and magnetic field was set up due to current flowing through this coil. So likewise here also, since I2 current is flowing, so flux will set up, and this flux will actually, according to Lenz's law, it will oppose this main flux, right? Say this is phi m, okay, So it will oppose this main flux. Why? Because according to Lentz's law, it will oppose the cause by which it has been produced. So the cause for this voltage induce is this flux. So ultimately it will try to oppose this flux. So what will happen? This flux will decrease, right? This will decrease. Okay. See, try to understand. This is very important concept. Okay. So this will start decreasing. Now, since this the strength of this alternating flux which was earlier set up in the core due to this primary winding current, now it will start decreasing. So what will happen? If the strength of this flux will start reducing, so due to this flux, actually this E1 and E2 were induced. So now since the strength of this flux is reducing, so gradually this induced EMFs will also start reducing, right? So what will happen? This E1 will reduce. Okay. See, now, so before going into details, first I must tell you that this E1 was actually opposing this V1. Okay? Okay. Why? Again, due to Lenz's law. So how can I write the equation, right? See here I can say that I naught is equal to V1 minus E1 divided by, suppose the resistance of this primary winding coil is R1. Very simple. So it will be, the I naught will be this one, V1 minus E1 by R1. Obviously these all are vector quantities. Okay, since they all are AC, alternating quantity. Fine. So now see, so earlier this E1 was more, right? At no load this value of E1 is more. So what will happen? This I1 will be less. So that I told you that no load current is actually it is 2 to 5% of the full load current, right? But now see, when we have loaded it, okay, so what will happen? So ultimate the result we are seeing that this flux is reducing due to this loading effect, right? And due to this flux this E1 is also reducing. So now if this E1 will reduce, what will happen to this I naught? It will start increasing, right? So actually this current will start increasing. Okay, this no load current will again, it will start increasing due to loading effect. Okay, so the more load we put here, the more load we put here, the more the less will be the flux and E1 also, right? So gradually if E1 will reduce, this I naught will actually increasing. Okay, this one. So due to this loading effect, the more load, it will start increasing. So start increasing, and it will uh, settle to a certain point. Suppose this is the full load. Okay, so it will reach a certain current. Say this is I1. Okay, so this I naught is no load current, or primary no load current you can say. In secondary there is zero current at no load. Okay, and now at full load this current has been increased up to I1. Okay, so see, it has been, and let us say that it has been increased by, this is the total current. So actually this I1 is composed of what? No load current as well as the current which is being counterbalanced from the secondary side, right? So say it has been increased by I1 dash. So what can I write? I can write that I1, this is primary current, or okay, primary winding current, this is equal to I naught plus I1 dash. Okay, so you see this I1 dash is coming from where? This is coming from the secondary side. Okay, it is the effect of load, okay, which is being reflected in the primary side. Okay, so there is a concept, I will explain that also. Okay, so this we cannot write, right? Because they are not means algebraically correct. It is actually vector addition. So it's better if you put a symbol here that I1 is equal to vector summation of these two. right? Where this is primary winding current, primary or simply primary current. Okay, this one is what? No load current, no load current, and this is what? This is uh, load current, load current reflected to reflected to primary. Okay, so this is the concept. So in exam, sometimes it is asked or in Viva that there is no electrical connection in between primary and secondary. Although if we load it in the secondary side, it is okay that the secondary current should increase. Okay, but why the primary current increases? Although there is no connection in between the primary and secondary. Okay, so now you can explain in this way that how it is dependent, how this primary winding current is dependent on the secondary winding current. So if you load it, ultimately the transformer will draw more current from the source. This is the proper explanation. Hope you understood. Okay, fine. Now, based on the concept we learned just now, I ask you to answer the question given on the screen in comment box. The question is, what is the effect of connecting load to secondary of transformer on the main magnetic flux in the core? Now, we will see how we can derive the EMF equation of a transformer. Okay, so see, in the transformer we see that in the core the flux, the nature of the flux is alternating one. So see here, I have drawn this alternating flux. This axis is showing the time axis and this is the flux axis. This is maximum flux. Okay, so this is one complete cycle. Fine. So we know that this, the time required to complete one cycle is the time period. Okay, this is time. So and time period, we have this relation, right? Time period is equal to 1 by f, where f is frequency. Okay, now see, if this is the time t complete, so what will be this time? Okay, so this time will be t by 2. Okay, this one, right? Okay, and what will be the time required, what will be the time required to uh, to change the flux from 0 to maximum? That means this one. Okay, so what will be this timing? This will be obviously in t by 4. Okay, this is t by 4. Clear? Okay, now see, let n1, what is n1? N1 is, you know, n1 is the number of turns in primary winding, number of turns in primary winding. Okay, primary winding. N2 is number of turns in secondary winding, secondary winding. Okay, this is winding. Phi m is what? It is maximum flux. Phi m is maximum flux, this one. Okay, this is the maximum flux. And f is what? Supply frequency, supply supply frequency. Okay, now see, according to Faraday's law of electromagnetic induction, EMF induced is what? EMF induced, EMF induced is equal to d phi by dt. That is rate of change of flux. Okay. So here, what is d phi? D phi is what? Change in flux. Change in flux. That is d phi. This is equal to, say, 0 to phi m. So what is the change in flux from 0 to phi m? The change in flux is phi m, means maximum value, that is the final value, minus initial value. So phi m minus 0 is equal to phi m. So this is what? Change in flux. Now, how much time it takes to change the flux from 0 value to maximum value? Okay, so that is what? Change in time. Change in time, or time taken to change from 0 value to maximum value. This is dt is equal to, it is how much? This is t by 4. Okay, t by 4. Fine. And we know that t is equal to 1 by f, so we can write it as, by putting the value of t as 1 by f, we can write that it is 1 by 4 f, because frequency will be given. Okay, so in terms of frequency we'll try to find out. Fine. Now, uh, what is the average EMF induced per turn? Okay, so this induced EMF is actually average induced EMF per turn we have calculated. Okay, so let us write average. Therefore, average induced EMF per turn is equal to how much? It will be d phi by dt, d phi dt, rate of change of flux, is equal to, put the value, d phi is phi m divided by, what is dt? Dt is 1 by 4f. So this is 1 by 4f. Okay, so it will ultimately give us 4f phi m. So this is what? Now, average induced EMF per turn. Okay, average induced EMF per turn. Now, what is the RMS value? Okay, we need to find the RMS value. We are interested. So we have a relation, right? We know that form factor. Okay? This is from uh, basic electrical engineering. Everybody knows it almost, that form factor. What is form factor? It is the ratio of, it is the ratio of, form factor is the ratio of RMS value, RMS value by average value, average value. Okay, and for sinusoidal function or sinusoidal signal, the value is actually 1.11. Okay, so using this relation we can easily find, the uh, rms value, rms value of induced EMF per turn will be equal to, from here, if you try to find the RMS value, it will be average value into 1.11. So 1.11 into average value. Now what is the average value? Average value is 4f phi m. So just write it 4f phi m. So it will give us 4.44 f phi n. This is average RMS value induced per turn. The formula is for per turn. Okay, so now if we try to find the voltage induced in primary. Okay, in primary. So okay, move to next page. Okay, so RMS value of induced EMF per turn is equal to 4.44 F5M. Okay, so this is the formula we get, right? Now we need to find the induced EMF in primary. Okay, that is E1. Okay, so what will be E1? What will be E1? E1 will be equal to, since we know the, see here this is the transformer. Okay, secondary winding, primary winding. Okay, so number of turns in primary winding is how much? N1. In secondary it is N2. Okay, so per turn value we know, in any turn, per turn value we have. Okay, we have found out already. So to find this E1, okay, this primary induced EMF, we know the per turn value and we know the total number of turns in the primary winding. So what will be the total induced EMF? E1 will be equal to, obviously, per turn induced EMF into N1. Okay, so this will give us E1 value, right? That is primary induced EMF. Okay, now for secondary induced EMF, what will be the value? E2 will be equal to 4.44 F5M. This is the per turn value. This one is the per turn value multiplied by total number of turns in secondary winding. So it will give us what? E2 is equal to 4.44 F5M and 2. This is what formula for secondary induced EMF. These two are very important formulas. Okay, and from here we can also justify the relation that E2 by E1 is equal to N2 by N1. You can easily tell from this. If you divide it from this by this, okay, you will get this E2 by E1 is equal to N2 by N1, because these all will be cancelled out. Okay, so these are the formula for induced EMFs, right? And this is the formula that induced EMF per turn. So this is the main formula. From here we can derive it. Okay, I hope you understand this. If you have any doubt, you can write it in comment box. Okay, I will try to solve it. Now, voltage transformer ratio. This is the symbol for transformer. Okay, where these two lines shows the core. Okay, and this is primary winding, this is secondary winding. Number of turns depends on whether it is a step up or a step down. Okay, that I will explain you, okay, in this, during this session. Okay, so say this is primary winding, the number of turns is N1. In secondary winding, the number of turns is N2. Okay, the voltage supplied here is, say, V1. Okay, and the output voltage is, say, it is V2. Okay, the output voltage which is available for the load is V2. Okay, so as we have derived from the above EMF equation, from the EMF equation of transformer, that N2 by N1, that N2 by N1 is equal to E2 by E1. Okay, so this ratio is equal, so we take this ratio as a constant, and it is constant since these two are constant values. Okay, so we take this as K, which is called voltage transformation ratio. Okay, this is K. Okay, call it as K. Okay, where K is actually a constant, the constant K is known as voltage transformation ratio. The constant K is known as voltage transformation ratio. Okay. Now see, if N2 is greater than N1, okay. So first case, if N2 is greater than N1, so what will happen? So then E2, what will happen? Then E2 will be greater than E1. It means the output voltage, okay, or see here we can call it as this is V2. I am showing this is V2. EMF induced is actually here E2, here it is E1. Okay, that we have already done. Okay, so what happens that in ideal transformer this E2 and V2 are equal. Okay, E2 and V2 are equal. Here E1, okay, E1 and V1 are not equal actually. Fine. So see here. So if E2 is greater than E1, what will happen? So this output voltage E2, this output voltage E2 is greater than this voltage. Fine. So this is a step up transformer. Step up transformer. Fine. Now if N2 is less than N1, it means E2 is less than E1. That means the output voltage is less than the input voltage. So this is a step down transformer. This is a step down transformer. Okay. And as I was telling that for ideal transformer, E2 is equal to V2, E1 is equal to V1, as there is no voltage drop in the windings. Okay, so therefore what we can write that E2 by E1 is equal to V2 by V1 is equal to N2 by N1. Okay, N1. So this is a relation, important relation. Okay, important relation. Okay, now since there is no loss in the transformer in case of ideal transformer actually. First we need to understand the concept of ideal transformer. So there is no loss. Okay, so in that case what will happen that whatever is the input power, the output power will remain same. Here I1 current is flowing, here I2 current is flowing. So what will be input power? Power input will be V1. What will be input power? It will be V1 I1. Okay, and what will be output power? It will be V2 I2. Okay, so since it is a lossless, okay, in case of ideal transformer there is no loss. Okay, so input power output power will be equal. Okay, from here I can write that V2 by V1 is equal to I1 by I2. Okay, this is another relation. Okay, so I can write here that this is equal to, means E2 by E1 is equal to V2 by V1 is equal to N2 by N1. So according to this relation, I can write that this is equal to I1 by I2. Okay, fine. So this relation is very important. Okay, we can utilize these equations in solving the numericals. Okay, you see, to remember, only current is in reverse order, right? Means I1 by I2. Rest remaining all are E2 by E1, means in numerator or all the secondary parameters, in denominator all the primary parameters except this current value. Okay, it is in reverse order. So in this way you can remember this. Okay, okay, thank you for today. Okay, let us see some numerical regarding this topic. Okay, see, the numerical is a single phase 50 hertz transformer has 80 turns on the primary winding and 280 turns on the secondary winding. The voltage across the primary winding is 240 volt at 50 hertz. Calculate number 1 the maximum flux density in the core, and number 2 induced EMF in secondary. Okay, so let us see how we'll solve. Okay, so to solve any numerical, the best way to write all the given parameters initially with all the uh, symbols, okay, which we generally used. So here in this numerical we can see that primary induced EMF is given. Fine. So primary induced EMF we generally, okay, so this is solution. So primary induced EMF is given. That means the value of E1 is given. Okay. So E1 is equal to E1 is equal to 240 volt. 240 volt it is given. Okay. And this is actually equal to V1 in case of ideal transformer. Here we have already discussed. Now the given parameter is primary turns. What is primary turn? It is N1. Okay, N1. It is given 80. Number of turn is 8. Fine. So now we will first find the maximum value of flux in the core. Okay, that is phi max. We will try to find the. So in numerical these two are given, and we need to find what the peak maximum peak value. Okay, that is okay. So using the EMF equation, what is the EMF equation? It is E1 is equal to 4.44 F phi or phi m, right? F phi or phi m, whatever. Okay, flux is given uh, into N1. Okay, so from here we can find this maximum flux, that is phi m. It will be equal to E1 divided by 4.44 F, okay, F phi N1. Okay, so see here, what is E1? E1 is given 240 volt divided by 4.44 into F is what? F is 50 hertz, it is given. Okay, so we can write here F is 50 hertz already given. This is the general uh, frequency in India. Okay, uh, F is 50 hertz. Now this the value of N1 you put. What is the N1? It is given 80. So if you solve this, you will get a value. Okay, this phi max. So what will be phi max? Calculate. It will give us a value of 0.0135. Okay, please check it. Okay, there it is. So unit of flux is Weber. 0.0135 Weber. Fine. Now, so we are asked to find the maximum flux density. Okay, that is number one. We need to find this V max. Okay, so for V max, we know that flux density is flux divided by area, cross sectional area. Okay, so let us say I am writing by A, and in the numerical the net cross sectional area of the pore is given. Okay, I forgot to write that also. Okay, so IA is equal to 200 square centimeter. Okay, it is given. So 5 max by A. Now see, you write the value of 5 max. It is 0.0135 divided by the value of A is in centimeter. We have to convert it in meter square. So it will be 200 multiplied by 10 to the power minus 4. Okay, and if you solve it, so let us solve it in the calculator. Okay, I'm solving. So it is giving 0.6757 Tesla. Okay, so this is first answer. Okay, now the second thing is you need to find the secondary induced EMF. So E2. How can you find the E2? You know the formula, right? E2 by E1 is equal to N2 by N1. So from that we can write that E2 is equal to E1 into N2 by N1. We know this E1 value, right? N2, N1 is also no. Okay. So what is the value of E1? E1 is how much? E1 is 240 volt. So 240 multiplied by N2 is given 280. Okay. In the numerical, it is given 280 turns in the numerical. So 280 divided by 80, it will give us 840. So 840 volt. It is the secondary induced EMF answer. Thank you. Okay. Here in right and given that N2 was actually 280. It is given. Okay. Thank you for today.